Hi, as part of this week's review video, today I'm going to be talking about code analysis and how to go from a function to its runtime. And I'm going to be talking about master theorem, how to use it and why it's pretty important. So let's start with some code analysis of this function. It's from your section handout, but you probably didn't have time to get to it during your section. What's going on in this function? Well, we're given two parameters, this doubly linked list of strings and this integer n. Now, you're probably all used to seeing n and saying, wow, that's what I have to pay attention to. It's going to be in terms of n. And most of the time that's true. But let's look at it for this one. So we see that we have a nested loop here, and that's probably going to be pretty important to our runtime. This outer loop is going through every string in our list. This is a for each loop. That's what that means. So it's saying we're looking at every string in our list. We know exactly what this inner loop is doing. We're going from 0 to n, and we're doing constant work. And we're not doing another function here that's just one, simple action. So this inner part is n. And so our runtime is going to end up looking like something times n. And what is this something? Well, like I said, we're going through every item in our list. So you could say this is the length of your list. I'll call it len for now. That's the length of your list. It's going to be end up length times n. Is that just n? Is length a constant? Well, the list is one of our parameters, so the length really could be anything. The length could be 0, the length could be 1, or the length could be way, way bigger than our n is. If our n is 1,000 and our list is 1,000,000 items long, you don't want to discount, that's not a million, you don't want to discount the length of your list. That's pretty important in terms of how your runtime is going to be. Sometimes it can be more important than the n itself. So we have to take that into account. We cannot call length another constant. It has to be a different variable. Now you can choose really what name you want to give to your variable, but I would prefer giving it another letter. Oftentimes the letter m is used. Don't ask me why, it gets confusing. N times m is kind of hard to understand if you're saying that out loud. But for this example, you could just use m. You could use k, you could use whatever you want. But generally you want it to be another letter. So that would mean that our runtime is m times n, because both of those parameters matter and have a large impact on your asymptotic runtime. So that's the answer we'll give. But obviously we'll accept k times n, we'll accept c times n, whatever, as long as you explain that that other letter means this, you're good. Let's do another problem. So this function, we see it's got three different parts. This one is saying if n is less than 10, return. You're done. Just return a number. And that really won't matter in the grand scheme of things. So we can probably look at that later. Now this one is interesting. If n is less than 1,000, call the function again with n minus 2. So you'll keep going down 1,000, sorry, less than 1,000. So you can start at 999, then go to, 997, and then so on and so forth. But that's really not doing another function. That's, as we saw, if you just do n and then n minus 1 and then n minus 2, or something like that, if you're not, like this 2 is not substantial in the grand scheme of things. So this can be broken down to n. So we can just say that this whole recursive, keep going down this recursive path, we can just say that's n. But it only ever gets called when n is less than 1,000. So when your initial n is less than 1,000, then we can say our function is on the order of n. But we want to figure out our asymptotic, sorry, I'm trying to erase these. We want to figure out our asymptotic runtime. So as n approaches infinity, and last time I checked, infinity is a lot bigger than 1,000. So what happens in our extremely large n case? Well, in that case, we enter here. And what's happening here? We'll keep dividing by 2. And as we saw, well, maybe you saw in last week's review video, if you keep dividing something by 2, that's a log base 2 runtime. So that's logarithmic. So this part becomes log of n. Of course, it's log of n until you reach n is less than 1,000. In that case, it's just 1,000, you could say. It doesn't really matter. It's a constant when compared to how big your other initial n was. So again, this middle part doesn't matter. That may be a little bit confusing, but just think about it like this. As n approaches infinity, what is your function doing? Don't think about anything else in terms of when you're listening to asymptotic runtime. When you want asymptotic runtime, you think about how improbably large your n is going to be. And in that case, your n is going to be way bigger than 1,000. So then you really want to just look at this case. And in that case, you have a theta of log n. Now let's move on to some master theorem. Now what exactly is it saying? Well, it's saying if you have a recurrence in this form, where you have a constant here and constants here, 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 and here, then you can apply this. And you can say, if log base b of a has some sort of relation to your c, your overall asymptotic runtime is going to be one of these three functions. And this ends up being super, super useful. So how do we use this? Well, let's look at this problem. Is it in the form we want? Let me erase some of these things that are being annoying. Is it in the correct form? Well, we have a constant here, we have a constant here, and here, here, and this is just 1 in front of your n squared. So that's another constant, and this is another constant. So it seems like we're in the right form. And now our important variables are a, b, and c. And in this case, our a is equal to 3, our b is equal to 4, and our c is equal to 2. Now we want to look at what's log base b of a. So log base 4 of 3. Now, if you remember from math, what does a logarithm mean? Well, it means that if this is equal to question mark, it means that 4 to the power of something or question mark is equal to 3. And we know that 4 to the 0 is equal to 1 because anything to the 0 is equal to 1. And 4 to the 1 is equal to itself, which is 4. So that means since 3 is between 1 and 4, the power that 4 is being raised to get to 3 is between 0 and 1. And if something's between 0 and 1, that means that it's less than 2, right? So log base 4 of 3 is less than 2. And what does that mean? We go up to here, this case, it's less than 2, so our overall runtime is going to be n to the c, or c is equal to 2, so we get theta of n squared. Now let's try another one. Looking at this one, again, let's match it up to our master theorem. We've got a constant here, oops, got a constant here, here, not here. This is a function. Log of n is not a constant. So therefore, master theorem cannot be applied here. What do you do in this case? Well, you probably write out a summation and then you reduce it to a closed form and then you do all the math stuff that you hate doing. So in this case, master theorem can't bail you out. But that goes to show how cool master theorem is. When it can be used, it can save you a lot of time. But really either method works, as we'll show here. So if you remember from section, you did this problem. You went from this recurrence and you went to this sum, which you hopefully had time to do in class. Which you may not have had time to do in class was also surmise that this becomes 2n minus n to the power of log base 6 of 3. So that's one answer. And now let's come up with our answer using master theorem. this won't go away. All right, let's come up with our answer using master theorem. So we have a constant here, here, and here. Our C is equal to 1, and our E is also equal to 1. So we've got constants everywhere. Now let's use master theorem. Well, our A is equal to 3, and our B is equal to 6. This means that we're going to be looking at log base 6 of 3. Now again, we've got one of those cases where since 6 to the 0 is 1, 6 to the 1 is equal to 6, this is going to be greater than, the answer to this is going to be equal to greater than 0 and less than 1. And if something's less than 1 and our C is equal to 1, that means that log base 6 of 3 is less than 1, right? Because we just said that. Makes sense. So that means, again, we go back to this case. And our theta of our runtime would be n to the 1, which is just n. Now, let's compare that to the answer we got using our summation. Well, this is equal to 2n minus n to the log base 6 of 3. As we just said, n to the or log base 6 of 3 is less than 1. So this is going to be definitely less than this part. So we can really just count that. That goes to 2n, and which means it's just theta of n, because 2n doesn't really matter. We get rid of constants in the grand scheme of things. So we can see that it matches up. Now, again, master theorem can't always be used if you don't have constants in the right places, but you can use it to check your work or to just find the answer in a form such as this. If you really want to be thorough, you can do the summation and the master theorem and make sure they both match up. Or you may be given a problem where they give you the sum and you have to use master theorem to check the answer of the sum. Point is, it can be really useful when you have it in the correct form. Hopefully this video helped. Thanks for watching.